Under special topics, I like to consider weak formulations for finite element methods, which is another special request. So let's go straight to that point. In the previous video, we had looked at the discontinuous Galerkin finite element methods. And here we'll look at weak formulations for finite element methods, which applies to both continuous and discontinuous finite element methods. So, straight up, the weak formulation is one of the central ideas behind the finite element method. And the main goal is to transform a differential equation written in its strong form into an integral form that requires fewer derivatives of the unknown solution. So we will then derive the weak formulation carefully and then connect to the Galerkin finite element method and discontinuous Galerkin methods. So straight up, we have the first part here. We start with the strong form of the partial differential equation, right? A strong form of a differential equation. So consider the one-dimensional Poisson problem where we have minus u prime prime of x equals f of x, and x is defined on the closed open interval 0, 1. So with homogeneous Dirichlet boundary conditions, so u of 0 is 0 and u of 1 is 0. Now, this is called the strong formulation. So what the whole setup here is called the strong formulation, and that is because the differential equation is required to hold pointwise at minus u prime prime of x equals f of x. Therefore, the solution must possess a sufficiently well-defined second derivative. So here, this is actually a differential uh, an ordinary differential equation. And minus u prime prime of x simply is this minus u prime prime of x equals f of x. Can also be rewritten as minus d squared u dx squared equals f of x. So it's a second order expression, and then it is equal to a particular f of x. So some kind of forcing term, if you like. So or some function of x, not necessarily that forcing term. So therefore, the solution must possess a sufficiently well-defined second derivative. So that's the deal. Now, why do we need a weak formulation? So, we have the strong formulation already given. Why do we have to now have a weak formulation of the same thing? So first of all, the strong formulation requires the second derivative u prime prime to exist. However, finite element approximations are often piecewise polynomial functions. So finite element approximations are usually piecewise polynomial functions. For example, a piecewise linear finite element approximation has the form u sub h of x equals a sub I plus b sub I of x inside each element. So as a result of that, UH prime of x will have to be B1 of x. And when we differentiate this with respect to x, so we get B sub I rather. And because this is constant, it goes to 0. And then second derivative will actually go to 0. And that happens inside each element. So finite element is all about you having a region and you break it down into elements, finite elements like that. And each element can then be approximated using piecewise polynomial functions. And that is exactly why the strong form has to be converted to we need a weak formulation of the strong form of the partial differential of the differential equation, not necessarily partial. Now, at element at element boundaries, so every element has a boundary, right? I think I gave a very good example previously, talking about the I gave an example previously, right? Talking about the whole idea of like a rod, maybe you have heat flowing in a rod and things like that. So imagine this scenario that you have, you have a rod from 0 to L. So you now divide that into portions like this. So these portions are called, so each of this is an element. So every element has a boundary with the next element, a boundary with the next element, and so on and so forth. So that's exactly the idea right here. So, and going by that, then at element boundaries, the first derivative can also have jumps. So, in having jumps means we have discontinuity, like what we considered in the first video. Thus, a piecewise linear finite element function generally does not possess a classical second derivative everywhere. So this creates a problem if we try to substitute u sub h directly into minus u prime prime equals f. So the weak formulation resolves this problem by reducing the differentiability requirement. So for the strong form, we need a strong differentiability requirement. So, but the weak formulation resolve this problem, but because the differentiability requirement is reduced. Now, let's talk about a test function now because it's actually a test function that makes the weak formulation possible. Now, let v of x be an arbitrary test function. Now, because the problem has homogeneous Dirichlet boundary conditions, we choose test functions satisfying v of 0 equals v of 1 equals 0 like that. So that means at both ends of the of the whole space, everything, so the beginning corresponds with the end, in short, and they're both 0. So it's more like heat flow, right? So heat flow at the start of it, at the beginning of a rod, is equal to heat flow at the end of a rod, and that is 0. So the corresponding function space then would then have to be v equals h sub 0 super 1 of 0 comma 1. That's on the whole domain like that. So for now, the important idea is simply that the test function v of x is sufficiently smooth and vanishes on the Dirichlet boundary. So this is vanishing because it goes to 0. Now, next we then go ahead to talk about, we have introduced the test function v of x, and then don't forget the expression we started with, minus u prime prime equals f. Now, we then go ahead and multiply the strong equation by the test function. So the strong equation is minus u prime prime equals f. So multiplying both sides by test function v then becomes minus u prime prime multiplied by v equals f multiplied by v. So that is the test function multiplied by the strong strong differential equation. I wonder why I keep saying partial. We then integrate over the entire domain. So we have to integrate this whole thing now. So we have integral from 0 to 1, then minus u prime prime is a function of x, then v itself is a function of x. We integrate with respect to x. And then for fv, right, where f is a function of x, v is also a function of x, we also integrate that with respect to x over 0, 1, which is the domain 0 to 1. Now, this is the first major transition that is happening here now. So we have a strong partial differential, a strong differential equation. Then we get a test function v of x, and we multiply every part of the equation by that, and then we try to integrate over the domain, over the entire domain 0 to 1. Now, the next thing we have to do now is to integrate by parts. So first of all, we have u prime prime v dx. We have to integrate this by parts. So the left-hand side contains the second derivative u prime prime. So, and for integration by parts, right, it is always good to choose, okay, like if you have a kind of generalization. So imagine that you have integration by parts is simply this, that you're integrating u dv, and that will give you uv minus integral of v du. Now, what that tells you is this now. So this u, you have to differentiate it to get du, okay? Then, apart from that, dv has got to be integrated to get this v that you see here, and it's the same as this v that you see here. So it means that anything you're choosing for as your u should be easily differentiable, and it is easy to differentiate something that it's clearly this u prime prime is a derivative, right? So it's clear this u prime prime is a derivative, so we can easily integrate it to get u prime, and uh, we can easily integrate this to get u prime, and we can easily, yeah, this should be something that is easy to differentiate, and then v dx can easily be integrated. Okay, I guess we can choose v for easy integration, but let's see how this goes. So we use integration by parts, right? So we have integration from a to b of p prime of x, q of x dx, and in that case now, it then has to become, so if you integrate p prime of x, you get px, and if you integrate qx dx, you get q of x like that. And so that is from a to b, and that is equal to integral from a to b of p of x. So p prime, that was a derivative here. So integrate that. So u prime can easily be integrated, actually. It can easily be. I I keep getting, okay, yeah. Well, let's keep going. So this is p of x, q prime of x dx. Now, the next one, we are setting p of x. We set p of x to u prime of x. So as you can see here, p of x is u prime of x. So that means that p prime of x is u prime prime of x. So for it to coincide with this kind of idea here. And then on the other hand, we have q of x set to v of x. So it means our q of x is this v of x right here. So we have set this up as a standard that we want to follow. And it is clear that if you have p prime of x, if you integrate p prime and you get of x, you get px and you get qx. Whereas if you differentiate q of x, you get if you so we integrate p prime of x dx, you get p of x. You integrate q of x, you differentiate q of x, and you get q prime of x. So that's the standard we have set for ourselves now. So in this case, p prime of x is u prime prime of x, and q prime of x is v prime of x. So because p of x is u prime of x like that, and q of x is v of x. So that means that p prime of x, when we differentiate this, we get u prime prime of x, and q of x, and when we differentiate, we get q prime of x, which is v prime of x. So therefore, we can say integral from 0 to 1 of u prime prime v dx. That can now become like this. So u prime prime, if you integrate u prime prime, you get u prime. So because you differentiate u prime prime to get u prime to get u prime prime. So it means if you integrate u prime prime, you get u prime here. And then for v dx now, so you have to, so v dx is here. So if you differentiate, so v dx will have to remain here like this, because if we integrate v dx, so if you differentiate v dx, right, v remains here, and then you have v prime right here. So I think the basic thing is just to follow this formula right here. So once you have p prime of x, q of x, so that means you have u prime prime, then v dx, and then integrate this, you get u prime, then this v remains the way it is here. And then, of course, since you integrate this, you differentiate v, and that is why here you now have u prime, v prime dx, like that. So from 0 to 1. So if you multiply both sides by -1, just to transfer the minus sign, so the minus comes here, and you have minus outside there, and this becomes positive. So that's the first thing we do here. But if talking about integration by parts, so in essence, if I'm going to do it in another way, so all I'm doing is for the left hand side, right, I have integral of 0 minus 1. So 0 minus 1. I mean 0 to 1, right? Okay. So if you don't want to follow that idea, right, we have integral of u prime prime v dx. So we need to integrate this by parts. So, and what we need to do here is this. We need to say, normally we use u and v, right? But in this case, we're saying this, we try to, because this one it's a derivative for sure. So we can try to integrate this. All right. And so we have to integrate u dx. On the other hand, we can then we can differentiate v on its own. So, and following the formula, right, it means that integral of u prime prime v dx, and that's from 0 to 1, that's the domain. So in this case now we integrate u prime prime dx. When we integrate u prime prime dx, we get u prime, right? And we multiply that by the v that was there already. So, and that is from 0 to 1, minus integral from 0 to 1. So now we have this u prime. We have this u prime, because remember the general formula. The general formula is something like this. You have integral of u dv equals uv minus integral of v du. So what that means is that in this case now, it is u that you differentiate. So uh it is u that you differentiate. That's why you have the u right here. So in this case, what we are differentiating is v. So in that case, and we are integrating u prime prime dx. So in that case now, if you differentiate u remains here, differentiate, integrate v, you get v here, and then the v also comes here. So in this case, we're integrating u prime prime to get u prime, and then the u prime also comes here. On the other hand, we differentiate v. So when you differentiate v, v prime comes here like that. So v prime comes here, and then you have that with respect to x. So in essence, we can then, so the other type, then we now multiply through by minus. So we have integral of minus integral from 0 to 1 of u prime prime v dx, and that is equal to um, u prime v from 0 to 1 minus, okay, I've multiplied now. So some things have got to change. Okay, guess I have to wait a bit for this. Okay, now we're multiplying through by minus, right? So we have minus of this side. Then for this now, and this is also minus u prime v from 0 to 1 plus integral of u prime v prime dx from 0 to 1 also. So that's what we have on that side. And we can continue on with the notes. Okay, so that's why we have this one right here. So in essence, u prime prime, we integrate, we get u prime prime, we integrate, we get u prime here, we get u prime here. V, we differentiate v, and then we get v prime right here, following integration by parts. So if you apply the boundary conditions now, so recall that the test function satisfies v of 0 equals v of 1 equals 0. Therefore, this expression, right, so this u prime v from 0 to 1, that means u prime v from 0 to 1 is the same thing as if you substitute 1 first, you have u prime 1, v of 1 equals, then substitute 0, you have u prime 0, v of 0. So we already know that u, okay, okay, well, v of 1 is 0, so 0 cancels this one automatically. V of 0 is also 0, so this whole expression is equal to 0. So everything here goes to 0. And then what do we have left? Minus integral from 0 to 1 of u prime prime v dx, and that is equal to integral from 0 to 1 u prime v prime dx. And then substitute this into the integrated strong equation, gives integral from, so if you substitute this into the integrated strong equations, right, we will then have so then we had u prime prime v dx, and then all of that. So that means we have integral from 0 to 1 of u prime v prime dx. So this u prime v prime dx right here, and that is equal to integral from 0 to 1 of f v dx. So since these two are equal, right, so we can say this actually now is equal to integral from 0 to 1 of f v dx. So if you substitute into the integrated strong equation, this is the integrated strong equation, if you still remember. So that minus of u prime prime v dx is the same thing as fv dx. So as a result of that, we can then have this expression here. So since these two are the same, then we can say integral from 0 to 1 of u prime v prime dx is equal to integral from 0 to 1 of fv dx. Now, talking about the weak formulation proper now, we have arrived at the weak formulation like that. So if you find u, which belongs to h sub 0 super 1 of on the domain 0 to 1, such that integral from 0 to 1 of u prime v prime dx is equal to integral from 0 to 1 f v dx for every v belonging to the same domain as u. So that's the weak formulation. So this is the weak form of the Poisson problem with minus u prime prime equals f. So minus u prime prime equals x equals f requires some strong differentiability, but this is the weak formulation of the same idea by introducing the test function v. So the crucial difference is that the strong form requires u prime prime, whereas the weak form only requires the first derivative u prime. Then let's talk about strong versus weak form now. So for the strong formulation, minus u prime prime equals f. That's what we have. So the second derivative appears explicitly here. But the weak formulation is basically preventing us having the second derivative. So we don't need to have, so even if u prime is not differentiable, we are still good to go when it comes to the weak formulation, because you have introduced a test function v. So for the weak formulation, instead of having u prime prime, we just need u prime. So integral from 0 to 1 of u prime v prime dx is simply the same thing as integral from 0 to 1 of f v dx. So only first derivatives of u and v appear in the weak formulation. Thus, the strong form requires u prime prime, while weak form requires only u prime. This reduction in differentiability is one of the main reasons finite element methods work so well. So weak forms requires reduction. It can do with some reduction in differentiability, while strong form cannot do that. And that is why we need weak formulation of finite element method. So now, why does H1 appear, right? The weak formulation involves U prime rather than U prime prime. So the Sobolev space, so the H1, right? The Sobolev space H1 on the domain 0, 1 consists, roughly speaking, of functions satisfying U, which belongs to L squared of 0, 1, and U prime also belong to L squared of 0, 1. Thus, we do not require a classical second derivative, basically. So for homogeneous Dirichlet conditions, we then use the Sobolev at 0 on the domain 0, 1. Informally, H sub 0 super 1 of on the domain 0, 1 is the collection of all U belonging to the Sobolev space H1 0, 1, such that U of 0 is equal to U of 1 is equal to 0. That is basically what that is. So therefore, the weak formulation allows a larger class of functions than the strong formulation. So weak formulation allows a larger class of functions than the strong formulation, in addition to the fact that it doesn't require the second derivative. It only requires first derivatives. So why do we introduce a test function? So the test function V allows us to convert the differential equation into an integral statement instead of requiring minus U prime prime of x equals f of x. At every point, we require integral from 0 to 1 of minus U prime minus f minus U prime prime minus f v dx equals 0 for every admissible test function V, right? Then the phrase for every V belonging to V is extremely important. This happens for every V belonging to V. So we are not choosing one particular test function. We require the weak equation to hold for every allowable test function. And then we go on to physical interpretation. So the weak formulation can often be interpreted through the principle of virtual work. So the weak formulation can often be interpreted through the principle of virtual work. The term integral from 0 to 1 of U prime V prime dx can be interpreted as an internal virtual work contribution. So the term integral from 0 to 1 of f v dx represents the corresponding external work. So it's more like we have internal virtual work equals external virtual work for every admissible virtual displacement V. So if you remember the first video, right, we're talking about the fact that if you have U minus, it means that there's a flow from the left side to the right side. But if you have U plus, you have a flow from the right side to the left side. That's talking about flow from one element to the other, because we're talking about finite elements and they have boundaries. So there are flows like that. So this interpretation becomes particularly useful when deriving finite element formulations for elasticity, structural mechanics, and fluid mechanics, and other physical systems. So then we go on to define the bilinear form. It is convenient to introduce a bilinear form A of U comma V, which is equal to integral from 0 to 1 of U prime V prime dx. So we also define the linear functional L of V, which is equal to integral from 0 to 1 f of V dx. So here now we have the bilinear form A as a function of U and V, which is integral from 0 to 1 U prime V prime dx. We also define another linear function L of V, which is integral from 0 to 1 of f of V f v dx. So the weak formulation can therefore be written compactly as A of uv equals lv, right? Like that for every v belonging to v. So for this Poisson problem, A of u comma v equals integral from 0 to 1 u prime v prime dx, and L of v equals integral from 0 to 1 f of v dx, like that. So for the Poisson problem, right, we have A of uv equals this and L of v equals that. That's what happens for the Poisson problem. So from the weak form to the finite element method, we're talking about weak formulation for finite element, right? So having done the weak formulation, so we have converted a strong form of a partial differential equation, which requires a strong derivative, to a weak form, which requires only first derivatives. So the weak formulation is still an infinite dimensional problem because V is equal to H sub 0 power sub 0 H1 sub 0 of on the domain 0, 1, and that contains infinitely many functions. So the finite element method replaces V with a finite dimensional V space, a finite dimensional subspace V sub H, which is a subset of V. So we now seek an approximation solution where U sub H belongs to V sub H now. So instead of having just U and V, we then have instead of having A as a function of U and V, we just have A as a function of U sub H, comma V sub H, which is equal to L of V sub H. For every V sub H belonging to V sub H, the subspace of the finite dimensional subspace of the infinite dimension space V. So equivalently, we can then say we have integral from 0 to 1 of u sub h prime v sub h prime dx, which is equal to integral from 0 to 1 of f v sub h dx for every v sub h belonging to vh. So it is the same weak form we have but now we are just only dealing with it in terms of subspace. So if we can now introduce finite element basis function, suppose the finite element space V sub h is now it spans phi 1, phi 2 up to phi n. Then the approximate solution can be expressed as u sub h of x, which is equal to integral from j equals 1 to n of u sub j phi sub j of x. If you remember in the first video, we dealt with this. So the functions phi 1, phi 2 up to phi n are the finite element basis functions. So you can choose whatever basis function like Legendre and co. So the unknown function u sub h of x then has therefore been replaced by the finite set of unknown coefficients u1, u2 up to un. So these are unknown coefficients. This is the key step that turns the PDE problem into a linear algebra problem, and that is what finite element is doing. That resembles the idea of Laplace a lot. So Laplace turns differential equations into algebra, or even integral equations sometimes into algebra. So algebra is easy to handle. Once you get the solution in algebraic form, you can then take it back to the context you started from. Then let's talk about the Galerkin method. In the standard Galerkin method, the test functions are chosen from the same finite element space as the trial functions. So the same finite element space as the trial function. And you know, the trial functions are like the backbone of the whole idea of weak formulation. So if you choose v sub h to be phi I, where I can be from 1 to 2 to n, so it means v sub h can be phi 1 up to phi n, then the weak formulation becomes integral from 0 to 1 of u sub h prime phi sub I prime dx, and that is equal to integral from 0 to 1 of f phi I dx. So relating that to where we are coming from. So since we can then say UH prime, the UH defined here is this now. So UH prime of x will have to mean the derivative of phi sub j of x. And this j may have to shift, right? Okay, so there, since UH prime is equal to summation from j equals 1 to n of u sub j phi sub j prime. So we obtain integral from 0 to 1 of this whole thing. So integral of this UH prime, which we have here, multiplied by phi sub I prime dx. And that is equal to integral from 0 to 1 of f of phi I dx, like that. So basically what we have done here is to talk this to replace UH prime with this its expression here. And in that case, we can derive the finite element matrix. So we now move the summation outside the integral. So to move the summation outside the integral, so this summation now, so summation of over uj comes out, and we have integral from 0 to 1 of phi j prime, phi I prime. So you have phi j prime phi I prime dx, and that is equal to integral from 0 to 1 of f phi I dx, phi sub I dx, that is. So then you can define the stiffness matrix entries by k sub ij, which we saw something like that in the last video too. So k sub ij is equal to integral from 0 to 1 phi I prime phi j prime dx. So k sub ij is this whole thing now. So if we define the load vector entries by fi, so fi is now integral from 0 to 1 of f phi sub I dx. Therefore, we have summation from j equals 1 to n of k sub ij, u sub ij to be fi, which is simply this. So in matrix form, we then have ku is equal to f. And this is the algebraic system solved by the finite element method. So at the end of the day, the finite element method ends up solving this algebraic expression right here. And this whole thing is just matrix like that. So it's more like we are looking for u and all that kind of thing. So what does the stiffness matrix mean then? So the stiffness matrix is defined by k sub ij that we defined up here. So this is the stiffness matrix up here. So the stiffness matrix is defined by k sub ij, which is equal to integral from 0 to 1 phi I prime phi j prime dx. So each entry measures an interaction between two basis functions. So the diagonal entries kii describe the contribution of a basis function interacting with itself. Then the off-diagonal entries kij, where I is not equal to j, describe interactions between different basis functions. So for the Poisson equation, The stiffness matrix encodes the derivative structure of the partial differential equation. So let's take a simple example here. So for a one-dimensional Poisson equation, consider minus u prime prime equals 1. So f of x now is simply equals 1. So not any other function. So it's a function of x normally, but then we simplify it here to make it just 1. This means you have partial minus d squared u d x squared equals 1. So 0 is less than or equal to x, less than or equal to 1. So with u of 0 equals, with u of 0 equals u of 1 equals 0, then the exact solution, if we solve this particular equation, the exact solution, u of x becomes like x into 1 minus x all over 2. So in that case, okay, can we even attempt to do that? This is a second derivative, second order, right? Um, yeah, so we get u sub x, right? U of x is x into 1 minus x over 2. When we solve this, the exact solution actually becomes this. Indeed, with if you split this up now, it's like you have x over 2 minus x squared over 2. So if you differentiate with respect to x, that means you have half x over 2 differentiates with respect to x, you get 1 over 2. X over 2 is half x, by the way. Differentiate with respect to x, you get half. Then x squared over 2. That means you get 2x over 2 when you differentiate. So 2 cancels out, so you have this x here. And u prime prime of x is simply equal to minus 1, which this one reduces to like that. Therefore, we then have minus u prime prime of x is equal to 1. So, but then the weak formulation will simply have to be integral from 0 to 1 of u prime v prime dx, and that is equal to integral from 0 to 1 VF or FV. Since F is 1 now, F has been given as 1 here. This f of x here is 1. So it means this is simply V dx. And that happens for every V belonging to the Sobolev space at 0 for on the domain 0 to 1, like that. So this is the weak formulation for that kind of situation. So now the question is, what is the Dirichlet boundary conditions? What if the Dirichlet boundary conditions are non-zero? So we've had 0 so far. So what if they are non-zero? Suppose u of 0, so before we've had u of 0 equals u of 1 equals 0. But now, what if u of 0 is a and u of 1 is b? So the weak formulation is still obtained by multiplying the PD by a test function and integrating by parts. So the important distinction is that the trial function must satisfy u of 0 equals a and u of 1 equals b. So whereas the test function still satisfies v of 0 equals v of 1 equals 0. Thus, the test function space remains homogeneous for v equals h, the Sobolev space on the domain 0 to 1. So the trial space is instead an affine space containing functions satisfying the prescribed boundary value. So even if the Dirichlet boundary conditions are non-zero, we still have that. So then we have Neumann boundary conditions. So consider minus u prime prime equals f. With Neumann conditions, u prime of 0 is g sub 0 and u prime of 1 is g1. So after integration by parts, of course, we get integration from 0 to 1 of u prime v prime dx minus u prime v from 0 to 1 equals integral from 0 to 1 f v dx, like we had before. So since u prime v from 0 to 1 is u prime of 1 v of 1 minus u prime of 0 v of 0, then what do we have? We then obtain integral from so these ones now, instead of having just 0, we now have g naught. So we then have integral from 0 to 1, this integral now, v prime dx, and that is equal to, so this whole expression now is, if you have, for this, u prime of 1 is g1, v1, okay, v1 is 0, so this one will still go. So v of 1, u prime of 1 is g1, and then we have v1 like this, and then this minus u prime of 0 is g naught, and we have v naught. Okay, so now we have so if you have, so this expression now, you can take it back here, and then we have u prime of 1, that's g1, v of 1, then minus g sub 0 v of 0 here, and then this is the f v dx that you had here normally. So based on this now, so thus we can then have integral from 0 to 1 of u prime v prime dx equals integral from 0 to 1 of f v dx plus G1 V1 minus G naught V naught. So instead of just having this, so normally with the other condition, these two would have gone to zero, but now we just have them in addition. So this demonstrates an important principle that Neumann boundary conditions naturally appear in the work formulation through boundary terms. So if you have boundary terms that are not vanishing, then we can actually have those terms added like this. So now, why is integration by parts so important here? So integration by parts performs three major tasks. First of all, it reduces the derivative requirement. We transform u prime into u prime by integrating, and then it transfers the derivative. So the derivative is moved from u to the test function. So we then have u prime prime. Instead of u prime prime v, we now have u prime v prime. So we have, instead of having a second order derivative, we can have two first order derivatives like that. Then it exposes boundary terms now. So these boundary terms reveal how natural boundary conditions enter the variational formulation. Therefore, integration by parts is not merely an algebraic manipulation. It is one of the fundamental mechanisms underlying the finite element method. So integration by parts is always useful. So let's look at the connections to discontinuous Galerkin methods, which the first video talked about. So the weak formulation becomes especially interesting for discontinuous Galerkin methods. So in standard continuous Galerkin finite element method, we know that V sub h is a subset of the Sobolev space h sub 1 on the domain omega. So the finite element approximation is continuous across element interfaces, but in discontinuous Galerkin methods, the approximate solution is allowed to be continuous. I mean, to be discontinuous rather. We saw that in the first video actually. So U sub h minus is not equal to U sub h plus, which is required in the continuous situation. So for at the element interface, this can hold. Therefore, V sub h is not necessarily a subset of the Sobolev space, on the domain omega in general. So this means we cannot simply rely on cancellation of all elements boundary terms. So then we also have element-wise weak formulation in discontinuous Galerkin. So suppose the domain is divided into elements. So the space, the domain rather, is the union of all the elements over K. So starting from minus u prime prime equals F now, we integrate separately over every element. So every element has its own thing. So we have summation over K for integral of K minus u prime prime v dx, and that's summation over the whole of K, that's integral over K f v dx. So now instead of having the straight thing we had now, so every element has its own thing, and that is the difference that we have when it comes to discontinuous Galerkin. So the boundary the boundary now contains, okay, integrating by parts on each element will now give this now. So integral this. So we have u prime v prime dx. It's more or less like what we had before, except that now we have this is happening for every element. So summation over k of the integral, then u prime v, just like before, except that we have it happening for each element, and then we have to sum it up for every element, and this also like that. So the boundary terms now contain contributions from every elements interface. So because the discontinuous Galerkin solution can be discontinuous, these interface contributions do not automatically cancel like we would get in other situations. Then we talk about jumps and averages because we are talking about discontinuous Galerkin. So at an interface, the solution may have two traces. We have u prime from the left element and u plus from the right element. I mean, u minus from the left element and u plus from the right element. So a typical jump is then defined by jump u is u plus minus u minus, and a typical average, which is the collection of u, that's u plus u minus all over 2. We saw that in the first video also. So similar definitions are used for derivatives and fluxes. We talked about derivatives and fluxes in the first video. So these quantities allow the discontinuous formulation to describe how information is transferred between neighboring elements, since there's no continuity normally. So talking about continuous Galerkin versus discontinuous Galerkin now. So the fundamental distinction can be summarized. The fundamental distinction can be summarized as follows. For continuous Galerkin, the approximate the approximation is continuous. So where UH minus is equal to UH plus. So there's free flow of information between on the element boundaries. So element interface contributions can often cancel naturally. But for discontinuous Galerkin, the approximation may be discontinuous where UH minus is not equal to UH plus. So interface terms must therefore be treated explicitly. So this leads to numerical fluxes, it leads to jump terms, average terms, and for many discontinuous Galerkin formulations, we have penalty terms. So thus the discontinuous Galerkin method can be viewed as a systematic extension of the weak formulation in which the equation is integrated element by element. So we can then have the complete chain from PDE to finite element method. So the derivation can be summarized as this. We have the strong partial differential equations or whatever differential equation you have. Then we multiply by a test function, say v of x. Then we integrate over the domain. Then we integrate by parts. Then we obtain the weak formulation, which now involves just not as strict derivatives as the strong form requires. So we obtain the weak formulation and then we choose the finite dimensional space, like 0, 1 that we chose the other time, or anyone you want to choose. Then you choose the basis or test functions, whatever you want the basis function to be. Then you then have Ku equals F. So for the discontinuous Galerkin, the crucial modification is you integrate by parts, element by element. So this part where you integrate by parts just for everything. So for Galerkin, discontinuous Galerkin, you multiply element by element, and that is why for discontinuous Galerkin, parallel computing is easy because everything happens within. There's a localization in every element, for every element. So this produces interface terms that must be handled explicitly. So far our key takeaways from weak formulation for finite element method, right? So we have some key takeaways. The most important ideas are the strong formulation. The strong formulation contains derivatives of the unknown solution explicitly. So for strong formulation, contains derivatives of the unknown solution explicitly. Then we multiply the PD by an arbitrary test function. We integrate over the domain. We use integration by part to reduce the derivative requirement. Then the resulting equation is the weak formulation. The Dirichlet conditions are generally incorporated into the trial and test spaces. Neumann conditions naturally appear through boundary terms. The finite element method replaces the infinite dimensional function space with a finite dimensional space V sub h. Then the Galerkin method chooses trial and test functions from the same finite element space. Then the resulting problem becomes a matrix system Ku equals F. So in discontinuous Galerkin methods, integration by part is performed element by element. Because discontinuous Galerkin solutions can jump across interfaces, interface terms involving jumps, averages, and numerical fluxes become essential for discontinuous Galerkin. Then, at the end of the day, we have a one-sentence intuition. The weak formulation takes a differential equation that requires the solution to be highly smooth, multiplies it by arbitrary test functions, then integrates by parts to reduce the derivative requirement, and converts the resulting variational problem into a form that can be approximated efficiently using finite elements. So, 2.2, the formula to remember. For the Poisson problem, now we have minus del dot del u equals F in omega. So, with homogeneous Dirichlet boundary conditions, the weak formulation will then be to find U belonging to the Sobolev space on the domain omega such that integral U dot V d omega is equal to integral over omega of F V d omega. So this is just a generalization of the whole thing. For every V belonging to the Sobolev space, H1 sub 0 of omega. So this formula of the fundamental starting points for the final this formula is one of the fundamental starting points for the finite element method. So for discontinuous Galerkin methods, the same philosophy is applied element by element with the resulting interface terms forming the basis for numerical fluxes and discontinuous Galerkin stabilization. So now we have our practice problems. I'm not sure if I should. Do I have time to do this? Okay, I guess I can do some. Okay, let's take some problems. Okay, so I'll answer question 4 and 17. So consider the boundary value problem. So So let me just show the problems. You can see 1 to 4 here. Consider the Robin boundary condition u prime of 1 plus alpha u of 1 equals g, starting from minus u prime prime equals f. Derive the corresponding weak formulation. So we'll try to do the weak formulation for this. In this case, now we have a Robin boundary condition. We'll talk about that. So I'll answer question 4 and then 17. So now you can see questions 5 to 8, all clear. Questions 5 to 8. Then you can see 9 to 12. All clear. 9 to 12. Then you have 13 to 15. All can be seen here. The next problem I'll be solving is 17. So you have 13 to 15. Then uh you can see 17 to 19 here. So I'll be solving question 17. Consider a two-dimensional Poisson problem. Minus del u equals f in omega. So starting from the strong form, derive the weak formulation using Green's identity. Clearly identify the boundary integral test. Clearly identify the boundary integral that appears. So, and this is 19, and then the last one, 20. So let's quickly take those problems and as we take this special topic home. Okay, so let's go now. So I go here, problem 4 now. Problem 4, which is actually a Robin boundary condition. Robin boundary condition. So here we consider minus u prime prime equals f for 0 less than x less than 1 with u of 0 equals 0, and then u prime of 1 plus alpha u of 1 is equal to g. So that's the Robin boundary condition. So what do? We have, so we multiply the differential equation. So this is the differential equation right here. Multiply the differential equation by a test function, satisfying v of 0 equals 0. So if we do that, we can have this now. So thus we have minus integral from 0 to 1 u prime prime v dx equals integral from 0 to 1 f v dx. So that's like the same thing we've done before, right? Normally we have minus u prime prime v equals fv, and then we integrate by parts and all that, and we end up having what this expression right here. So, and we have 0 to 1 because the domain itself is 0 to 1, like that. So with that in place, integrating by parts, integrating by parts gives, so for the whole expression now, so as we know, we are going to have, so this power, we are going to reduce the derivative requirements. So instead of having second derivative, we can have just two first derivatives. So at the end of the day, we have integral from 0 to 1 u prime v prime dx minus u prime v integral from 0 to 1 equals integral from 0 to 1, not integral now, u prime v from 0 to 1, then integral from 0 to 1 of f v dx. So just exactly what we did the other time. So just about partial differentiation for all of that. So with that in place now, since v of 0 is equal to 0, so here we are going to have, since v of 0 is equal to 0, we know that u prime of v from 0 to 1 is actually expected to be u prime of 1 v of 1 minus u prime of 0 v of 0. So since v of 0 is 0, so this is 0, so everything here is gone. So we have u prime of v from 0 to 1 left with u prime of 1 v of 1. That's all we have left. And since that's all we have left, we then have we then say therefore so this u prime v prime and all of that now. So all of that can be generalized. Uh, okay. So let's see. That's still problem four, right? Robin boundary condition. Problem four. So U prime, okay, so since we have this in place, right? We just have integral. So integral from 0 to 1. This is integral from 0 to 1, u prime, u prime v prime dx minus, so minus u u prime 1 v of 1, u prime of 1 v of 1, like that. So, and with that in place, then we have the other side, integral from 0 to 1 of fv dx. So, in that case, we have the boundary condition, which I think we need to invoke at this point. So the boundary condition, it's u prime of 1 plus alpha u1 equals g. So u prime of 1 is equal to alpha u of 1 is equal to g. Um, so okay. Therefore, we have u prime v prime dx minus u prime 1 v of 1 equals integral from 0 to 1 of fv dx. So from the Robin boundary condition, from the Robin boundary condition, we know that u prime of 1 is equal to g minus alpha u of 1. So because here now u prime of 1 is here, so from the Robin boundary condition now, we can make u prime of 1 the subject of formula. So u prime of 1 can be g minus alpha u minus 1, alpha u of 1, right? So with that in place, then if we substituting 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 this into the weak equation, into the weak equation gives integral from 0 to 1 u prime v prime dx minus, so here we have uh, in, uh we have u prime of 1 into v1. So, and we know u prime of 1 is g minus alpha u of 1. So that's g minus alpha u g. So g minus alpha u of 1 multiplied by v1. So g minus alpha u of 1 multiplied by v of 1. That is integral from 0 to 1 fv dx. So rearranging all of that now, we then have integral from 0 to 1 u prime v prime dx. So if you expand this now, we have okay, let me go step by step, right? So if you open this up, okay, so this is minus g, so minus gv of 1, so minus gv of 1, then plus alpha u of 1, v of 1, that is integral from 0 to 1 of fv dx. So we can rearrange all this still to be integral from 0 to 1 of u prime, u prime, v prime, u prime, v prime dx plus alpha plus alpha u of 1, v of 1 is equal to integral from 0 to 1 f v dx plus this g can go here. So v of 1 like that. So we have this expression right here. So we have this expression now. So, and that happens for all admissible, for all admissible test functions v, all admissible test functions v. Therefore, the bilinear form is a as a function of u comma v is equal to integral from 0 to 1 u prime v prime dx plus alpha u of 1 v of 1. So as you can see on this side here. So with that in place, so with all that, we then have okay, I think that should bring that to a closer. Let me see. Okay, so we have that now. So we have alpha, therefore the bilinear form is this now. U prime, v prime dx plus alpha u of 1, v of 1. So, and the linear functional is L of v, which is equal to integral from 0 to 1 fv dx plus gv of 1. That's this other side now. This other side of the expression. So what that tells us is that the important observation is that the Robin boundary condition, the important observation, the important observation is that the Robin boundary, the Robin boundary condition contributes contributes to both the bilinear form, to both the bilinear form, to both the bilinear form and to the right hand side and to the right hand side. Yeah, I think I want to stop here. I was thinking I'll do question 17, but I think I'll just stop here and let that be. All right, so let me know how helpful this is for you. But before we do all that, let's see the questions once more so you can try your hands on them. Again, see, you have question. So you have 1 to 4, question 1 to 4, 5 to 8, 9 to 12, 13 to 15, 16 to 19, and then 20. Yeah, so let me know how helpful this is for you. If there's something else you'd like me to try out, feel very free to let me know. If you have subscribed to the channel already, I thank you very much for doing that. If you have not subscribed, this is a good time to go ahead and subscribe. As you subscribe, you can also click on the notification bell so you can always get alerted each time a new video is released. Having done that, you can become a member of this channel by clicking on join. That gives some special privileges, which you will see as you click. Ultimately, don't forget to comment, like, and share so that more people can have access to the great content I have going on here. Till I come your way again, keep doing math right. Bye.